Good afternoon and welcome to Webinar Wednesday. Today we are joined by Ed Mireles, Innovation Manager at AllParts Medical. Webinar Wednesday would like to thank our sponsor, AllParts Medical. AllParts Medical provides OEM replacement Dunley and Phillips parts from its 158,000 square foot facilities in Nashville, Tennessee. In addition to parts sales, AllParts also provides customers an extensive array of in-depth training classes and technical support before and after the sale. An ISO certified quality management system helps deliver an industry-leading warranty rate for parts across multiple manufacturers and multiple modalities. For more information, please visit allpartsmedical.com. Just a quick reminder to save the date for our 2024 Spring MD Expo. We're headed to the M Resort Spa Casino in Las Vegas from April the 7th to the 9th. So please join us for 3 days of education, networking, and the latest advances in medical technology products and services. For more details, please visit mdexposhow.com. Okay, I just want to offer some congratulations to the finalists for the first annual Tech Choice Awards. TechNation is honoured to be part of the first awards that are 100% nominated by and voted by the HTM industry. All the finalists have been contacted and voting is open online through January the 12th. So please visit onetechnation.com/Tech Choice Awards to vote for all categories. Winners will be announced in the March issue of TechNation. Today's webinar is eligible for 1 CE credit from the ACI, and you can attain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Let's kick off today's webinar by giving away one of our Webinar Wednesday t-shirts to the attendee that can tell me the answer to the following trivia question. What beverage company has been using Santa Claus in its advertising since 1931? Answer now using the questions feature on your dashboard, and I'll reveal the answer at the end of the webinar. We'll be wrapping up today's presentation with a live Q&A, so please submit your questions anytime using the questions feature on the webinar dashboard. As I mentioned earlier, our presenter today is Ed Mireles, and he will be discussing MR Introduction, a brief history, MRI safety and system functionality. Ed, you may begin whenever you're ready.
Okay. Hello, my name is Ed Mireles. Today I'm going to be providing you with an introduction to MRI. This webinar is also going to include a brief history of MRI, MRI safety, and also MRI system functionality. So I'm a graduate of Texas A&M with a degree in EET. I started my career with RP Kinchlow in Dallas, Texas. I then moved to North Carolina working with King's Medical Group for a short time before I started working for Philips Healthcare in the multi-vendor group. I transitioned from field service to my current position as multi-vendor MRI modality manager, and I've developed some of the training material that has been used for basic MRI training to current MRI products. And I'm going to be going over several sections. Part 1 is a very brief history of MRI development. Part 2 will cover MRI safety. Part 3 provides an overview of MRI basics. Part 4, I will discuss the various subsystems used in MRI. Part 5 covers MRI imaging. Part 6 shows some image artifacts, and Part 7 will be concluding. So Part 1 is a brief history of MRI. So many researchers contributed to the development of MRI. Paul C. Latterber is credited for the invention of MRI imaging. He developed a method used to encode spatial information into an MR signal using magnetic field gradients in September 1971, and Peter Mansfield refined the techniques used in imaging acquisition and image processing. They were both awarded the Nobel Prize in Physiology in 2003. Latimer published the first NMRI images in 1973 and the first cross-sectional image of a living mouse in January of 1974. Raymond Damadian obtained the first image of a tumor in the thorax of a mouse in 1976 and the first MRI body scan of a human on July 3, 1977. John Mallard led a team that built a full-body scanner at the University of Aberdeen in the 1970s, and on August 28, 1980, he obtained the first clinically useful image of a patient's internal tissues. Paul Bottomley built the first high-field device, a 1.5T Tesla system, in the GE Research Center in Schenectady, New York. This led to the 1.5T MR product line. MR systems are primarily used in hospitals and imaging clinics, but they're also installed in specially built portable trailers. They're used for emergency care, neurology, angiography, and for pathological imaging. They do not generate ionizing radiation such as X-ray or CT. Since they are used to scan soft tissues, the MRI is able to distinguish the differences between similar but not identical tissues. A Tesla is a unit used to describe magnetic flux density. A smaller unit of measure for magnetism is called a Gauss. There are 10,000 Gauss in 1 T. Compare this to the Earth's magnetic field of 0.5 Gauss. The 1 T magnet is 20,000 times stronger than the Earth's magnetic field. There are different types of MRIs that are currently in use. The one shown here is an example of a closed-bore magnet manufactured by Siemens called the Magnetome Avanto 1.5T MRI. Other specialty magnets are also used for patients that are unable to enter the closed-bore magnet due to claustrophobia. An example of this type of MRI system is shown in the photo. These are called open-bore magnets. While they're examples of open-bore magnets with field strengths up to 1 Tesla, they are generally considered low-field systems, and most do not require cryogens. High-field magnets are 1.5 T or greater and require cryogens to maintain the superconductive magnetic field. An example of the strength of these magnets is shown on the next slide. This is a patient bed that is stuck to a high-field MRI. Part 2, MRI safety. To work around an MRI, you should be familiar with the MR-specific safety guidelines. This slide provides information on some of these. Please make note of these health-related guidelines. Notice that one of these guidelines is that a pregnant woman should stay out of the magnetic field. While this is a safety guideline, there have been no proven risks to the mother or unborn baby from MRI exams. If you're an FSC providing service, always use the appropriate non-magnetic tools for working around MRI. Use the phantoms that are provided and specific to each image quality check for the system and coils. As an engineer, you are not trained to image patients or people, so do not do this. Be aware of the different controlled access areas. There are restricted access warning signs at the doors and entrances to these areas. The customer will be aware of what can and cannot go into the scan room area. As previously mentioned, if you're going to be working on the MRI, ensure that you have tools that are allowed to go into the scan room safely, such as titanium hand tools or similarly non-ferrous tools. Cryogens are used as coolants in the MRI magnet to bring the internal vessel temperature to near absolute zero due to their extremely low temperature characteristics. In older MRI models, liquid nitrogen was used, but in newer, more modern magnets, liquid helium is used to maintain the superconductivity of the MRI magnet. 1 liter of helium liquid will convert to 750 liters of helium gas. I'm sure that at least some of you have heard of an MRI magnet quench. A magnet quench is caused when excessive heat is applied to the coils in the magnet vessel. A magnet can quench from a variety of factors, but in case of emergency, it can be quenched by pressing the system's emergency rundown button. Remember the helium conversion from 1 liter of liquid to 750 liters of gas. This causes excessive internal pressure of the magnet vessel. To prevent damage to the magnet, there are specialized discs in line with the magnet vent called burst discs. They're usually made from a ceramic material and are rated to fracture or break under high pressure. This allows the helium gas to escape while keeping the magnet safe from damage. A quench recovery is a costly process and can range up to and over $100,000 to bring the magnet back to scanning capabilities. There are many examples of MRI quenches that can be found on YouTube. Accidents can happen, so please use caution when working around an MRI. Part 3, MRI Basics. These are the steps in a basic process used to create an MRI image. Each step will be discussed in more detail. First, a patient is placed into superconducting magnet. Second, the magnet causes the trillions of subatomic particles in the body to align. Third, a radio frequency pulse is transmitted to the patient. This momentarily interrupts the magnetic alignment. This interruption changes the magnetic field, which results in a small electrical signal. This small signal is received by a coil, sent to an image reconstruction device via receivers, and delivered to the host computer in the form of an image. So the first step of creating an MRI image is for the patient to be placed into the superconducting magnet bore. This is done using a patient table made for the system being used. When a person is placed into the magnet, atoms within the anatomy begin to align in the direction of the magnetic field. An atom contains 3 subatomic particles called electrons, protons, and neutrons. Protons and neutrons are only found in the nucleus of an atom, while electrons circle the nucleus in an electron cloud. The fundamental properties of protons, neutrons, and electrons are as follows. Nuclei have a net nuclear spin, which is a complex sum of the proton and neutron spins. Nuclei of MRI active atoms have a non-zero nuclear spin. All particles in atoms have spin. Spin is an intrinsic property of atomic particles, just like charge and mass are intrinsic properties. The spin of the particles can no more be increased or decreased than can its mass or charge. Electrons, protons, and neutrons all rotate or spin. Each particle spins on its axis, generating a magnetic field. Electrons have a larger magnetic field than other particles. In fact, the magnetic field for protons and neutrons are so weak they have little effect. The sum of the spins of all the particles in the atoms, known as net nuclear spin, contributes to the strength of the magnetic field used in MRI. Since the human body is composed primarily of water, the hydrogen atom is the most prevalent one available. The hydrogen atom spins at a natural rate while in the magnet, but can be influenced by using external magnetic fields. When the main magnetic field is applied, the hydrogen atoms have two possible energy limits. One energy limit is said to be in favor of the magnetic field and the other is against it. If you could examine 1 million hydrogen nuclei at 20 degrees Celsius, by about 500,002, about 50% of the spins align with the magnetic field in a low energy state and parallel to the magnetic field. The remaining 499,998, again about 50%, align against the field in a high energy state and anti-parallel to the magnetic field. The total energy available is a dot product of the vectors and is very tiny. This is why copper is used to shield MRI rooms. It keeps extraneous signals out so that the equipment will mainly focus on the MRI signal. The slight imbalance between these two states is what is used in MRI imaging. Hydrogen atoms will precess at a specific frequency, the system resonant frequency, which is approximately 63.86 megahertz in a 1.5 T magnet. The concept that is generally used to describe the atom alignment in a magnetic field is technically not correct. The spins will not align with this field, but it is easier to talk about and to be understood when explained in this manner. Atoms will precess at the angle they were in when the magnetic field was applied. Again, the atoms spin and precess about their axis at the system's resonant frequency. For a 1T system, this is around 43 megahertz. A 1.5T is around 64 megahertz, and a 3T is around 128 megahertz. The precession of the spins can be compared to the inner and outer rings of a gyroscope. The precessional frequency rate is determined by the atom's intrinsic nature, its own magnetic strength relative to its bonds, and the strength of the magnetic field. The rate of the spin is the resonant or Lamar frequency. Because the protons spin, it has angular momentum and produces a small magnetic field. Each of the trillions of hydrogen atoms in the human body and their spinning protons create a magnetic field. The magnetic field of a single proton cannot be measured, but all of the protons together create a net effect or signal which can be measured. This signal can then be manipulated to improve its strength through the use of radio frequency to excite the protons and gradient fields to vary the strength of the magnet in specific areas. So an RF pulse is transmitted to the patient, which momentarily interrupts the magnetic alignment of the protons. To obtain the imaging slice position, a gradient field is applied in 3 coordinates, x, y, and z. When a slice selection gradient field is turned on, it adds or subtracts from the main field in the region of interest. This changes the precessional frequencies of the proton nuclei. A shaped RF pulse is transmitted at the resonant frequency the same time the slice gradient is turned on. Only those protons precessing in a narrow range around the resonant frequency are excited or rotated by the pulse. The interruption of the hydrogen atom's magnetic alignment results in a very weak electrical current. This is the MR signal. Radio frequency coils or antennas are then used to detect these signals in the magnet enclosure. There are 2 main methods to increase the MRI signal. One is to reduce the temperature to absolute zero, minus 273 degrees Celsius, so that all the nuclei align. In this state, all the spins would occupy the low energy state, but turning the patient into a popsicle wouldn't be a safe alternative. The other method for increasing signal is to increase the field strength of the magnet. If the field strength of the magnet is doubled, the MRI signal would be quadrupled. If the field strength is halved, the MRI signal will be reduced to 1/4. Lower field strength systems such as 0.2 Tesla and 0.5 Tesla systems have longer scanning times to compensate for their smaller signal. The acquired signal is then transmitted from the RF coil using RF receive lines to the image reconstruction computer and finally to the operator host PC where it is displayed. This is a very basic explanation of what occurs during image acquisition. There is a lot more interaction going on and would take a lot more time to explain than what is allotted. Part 4, MRI subsystems. This is a generic breakdown of the 3 areas used for the MRI equipment. The first is the system operator area, which has the MRI host computer and viewing station. The second is the equipment room with the required system components. The third is the MR magnet, which is an RF shielded room to prevent external RF noise and also prevent artifacts from showing up in the image. Starting in the scan room or magnet room, we have the main magnet enclosure, which houses the superconducting magnet, the radio frequency coils, the gradient coils, and a cooling or refrigeration system. The superconducting magnet generates the static magnetic field required for polarization or alignment of the body's protons. The cooling system surrounds the magnet and maintains it in a bath of liquid helium at 4.2 degrees Kelvin, or minus 452 degrees Fahrenheit. The MR magnet has several components, the primary one being the magnet itself and the refrigeration section. The refrigeration systems used can be either 10 Kelvin models or 4 Kelvin models. The first is not able to recondense the helium gas into a liquid, therefore it has a higher helium boil-off or loss than the 4K magnets in which the gas can be converted back into a liquid. Magnets of this type are said to be zero boil-off systems. This illustration does not show this very well, but the radio frequency or RF body coil that is mounted in the magnet bore contains loops of wire that transmit an RF signal to the patient and receive signals emitted from the patient. The signal is sent to the system cabinet for processing and reconstructing into an image. In addition to the coils inside the magnet, other coils such as head, knee, or spine are attached to the patient to pinpoint the specific anatomy to be scanned. There are many types of RF coils available. Each are designed for a specific part of the anatomy. There is also a gradient coil installed in the magnet bore. The gradient coil is a large cylinder made of fiberglass and epoxy. There are copper strips embedded in the coil that make up the X, Y, and Z gradient axes. They produce gradient magnetic fields that adjust the strength of the magnet in certain areas to help define the image plane and the slice thickness of the image. The penetration panel, or pin panel, is a connection panel that provides a point of entry for the cables coming from the equipment room into the scan room. This is used to allow a pass-through point for these cables, preventing stray RF from entering the room. The patient handling subsystem consists of the patient table and the components related to patient handling, comfort, and safety. Each OEM has its own method of patient transport and positioning. Some patient handling subsystems are able to be detached from the magnet, while others are fixed tables which cannot be moved. The equipment room contains the system control section, which processes the data from the scan, the RF amplifier section that directs the RF signals, and the gradient amplifier section where the gradient field is adjusted. The components inside of the RF amplifier section produce the radio frequencies that excite the patient's hydrogen protons. They are also used to maintain communication between the RF subsystem and the system control section. The RF amplifiers are used to amplify the signal generated by the transmitter module, which are then sent to the MR scanner. Specialized RF coils, such as body coils or certain head coils, are able to both transmit and receive RF signals and can apply these signals to the patient. The gradient section contains 3 gradient amplifiers used to produce calibrated magnetic field changes based on digital input in the X, Y, and Z coordinates. Gradient amplifiers are high current devices used to determine the slice position, thickness, and orientation based off the scan protocols used. The components in the system control section are used to manage the collection and processing of all the signal data from the scan. Each OEM also has its own method for controlling the scan sequencing. The parameters used for the scan are provided by the MRI tech when the scan protocol is set up. These parameters are transferred to the system control section either via LAN or fiber optics. The power distribution PDU unit distributes electrical power to the various subsystems. The PDUs for the different OEM equipment models can be located in different areas or cabinets, but will always be in the equipment room. The operator workspace is the interface between the scan technician and the system. The technician enters the patient's information and sets up the scan protocols that are used based on the anatomy to be imaged and moves the patient into the scan area of the magnet. The system OEMs use a variety of host computer models. At this time, the more prevalent host computer models are provided by Hewlett-Packard. Various hardware components that make up an MRI system can be a mix of components currently in production and those that are no longer being manufactured. One of the first challenges in servicing a system is to correctly identify all the hardware configurations, including any upgrades that might have been made. Part 5, MRI imaging. When I speak of using RF to excite a specific area, it is the hydrogen molecules in the body that are being manipulated to generate the signal that is used. As I have mentioned, the body is largely composed of water molecules. Each water molecule has two hydrogen nuclei or protons. When a person is inside the powerful magnetic field of the scanner, the average magnetic movement of many protons becomes aligned with the direction of the field. A radio frequency transmitter is briefly turned on, producing a varying electromagnetic field. This electromagnetic field has just the right frequency, known as the resonance frequency, to be absorbed and flip the spin of the protons in the magnetic field. After the electromagnetic field is turned off, the spins of the protons return to thermodynamic equilibrium and the bulk magnetization becomes realigned with the static magnetic field. During this relaxation, a radio frequency signal is generated, which can be measured with received coils. MRI is used to image soft tissue due to its water component, not bone. Since bone does not have an abundance of fluid, it cannot be imaged properly. The illustrations appear to show bone just fine, but the bone is actually outlined from the soft tissue surrounding it. All of these devices work in harmony with each other. Timing is very critical in order to produce an image, but when everything is working properly, the resulting images are extremely detailed. Part 6, MRI image artifacts. Artifacts can be defined as signals in an image which do not accurately reflect the anatomy under investigation. Artifacts can create two fundamental problems: unreadable images or readable images but are masking pathology in question. Artifacts can be categorized into three general groups. Hardware related, a service engineer will generally address these. MR physics, known MR phenomena can be explained and addressed by user by adjusting the protocol used. Patient related, known artifacts that can be addressed by the user. Any system imperfections or malfunctions may cause artifacts. These can be eliminated by machine adjustment or repair. Some of the possible artifacts for malfunctions are listed below. Zipper, corduroy, and ghosting are the most prevalent hardware artifacts. Artifacts can also be caused by RF frequencies leaking into the scan room or accidentally brought in with non-conforming monitoring equipment or even faulty light bulbs. Ghosting can also be caused by patient motion while scanning. This is an example of a zipper artifact caused by RF noise interference. This external interference can be caused by RF leaking into the scan room through defective room shielding at frequencies that are similar to the system frequency. This is an example of a corduroy artifact which can be caused by problems with the gradient amplifiers. They are usually seen as wavy lines in the background of the image and continuing through the entire image. Patient motion artifacts are similar to ghosting artifacts, but are not caused by hardware, but as the name implies, by the patient moving while being scanned. Common failure items for MRI include host computers or reconstruction computers, RF amplifiers, gradient amplifiers, RF coils, cold head and cold head compressor, which is part of the refrigeration section, and patient table issues. Do you want to know more? At AllParts, we can train you to service the systems shown in the table, from the basic principles of MRI to GE and Siemens MRI service. We will now have a short question and answer session.
Thanks so much, Ed. We've got some questions come in. The first question is, are the 4K magnet models the most efficient when it comes to helium usage?
So the 4K right now are the most efficient, but there are some other models that are called cryogen-free magnets that are being produced by Philips right now. I think Siemens has a low field one and Philips has some high field ones. And those are the ones that are the most efficient.
Okay, just leading off on the helium again. Does the helium ever have to be topped off, or does it only need to be refilled when there's a quench?
Well, there's several factors when that happens. So there will have to be a refill done, and hold on just a second. Let me grab something right here. So, can you say the question again? I got sidetracked on something.
No problem. Does the helium ever have to be topped off, or does it only need to be refilled when there's a quench?
No, it does have to be topped off. Okay, so there is a magnet monitor that will monitor the helium levels inside of the magnet. And even though they're called zero boil off magnets, nothing's truly zero boil off unless you get one of these helium free or cryogen free magnets. Um, so everything has to be perfect in order for it to work properly. The chiller is a big issue. If those ever shut off, it'll cause the cold head compressor to shut down. And when that does, it in turn causes an increased pressure in the magnet vessel. There are some safety devices in there that allow any excess pressure to bleed off, not just to burst this, so it'll actually vent for a little while. That venting will cause helium loss. So yeah, so most magnets will have to be filled at least once every year or so, depending on the refrigeration conditions.
Okay, so when is the MRI equipment turned off? Does the magnet turn off also?
No, so that's the standard answer. No, the magnet's always a magnet, even when the system's turned off. It's not very practical to ramp down a high field magnet because of the high cost of helium, liquid helium right now. So no, it's not very practical to do that. There are some low field magnets that can be ramped down when the system's turned off. These type of systems are used more in a clinical environment and really not in hospitals. But a safe practice around MRI is always to assume the magnet is on.
Okay, thank you. So does the radio frequency transmitted by the equipment interfere with other hospital equipment?
No, that's the purpose of the shielded room, the RF shielded room. It keeps the radio frequencies generated by the system inside the scan room, and it prevents any external RF energy or, sometimes some of the equipment that's used around the hospitals can cause this RF interference. But it is in that shielded room. The shielded room is called a Faraday cage. That's going to isolate any RF energy from the external environment, and it's also going to prevent any external noise from entering the MR scan room. That can generate image artifacts, as I said earlier.
Okay, so why was MRI also referred to as NMRI?
Well, I think I said something in the presentation concerning N. N stands for nuclear, and MRI is nuclear magnetic resonance imaging because of your using the atoms and emissions from your nuclei that's placed in the magnetic field. But so they did away with the N because during the Cold War, the term nuclear was considered a bad thing because of patients' concerns over the dangers of nuclear energy and radioactivity. So about in the mid 80s, it was dropped from the name. So instead, it's being referred to now, what we know it as is magnetic resonance imaging. This is just to make the term more patient friendly.
Okay, and this is going back to the presentation too, is on the slide for part 6, MRI image artifacts, what caused the artifact that was shown?
Yeah, that was a pretty interesting one I found online. That was caused by hair implants. It must have had some sort of metal in them, but any kind of metal in the MRI bore can cause this type of artifact. It's called a susceptibility artifact. It may not be as dramatic as what I showed it for the drama, you know. So during the screening process with the MRI technician and with the patient, they're asked to take out any metal objects like earrings, piercings, anything from their body. They're also asked if they have any metal embedded in their body. So dental work is a big issue when you're doing head scans, so they do need to be aware of that. This can cause a significant distortion in the image, and well, simply because it's metal and they're interfering with things. So um, it's it'll create a distortion in the image.
Okay, another question here is, what equipment is used to calibrate the RF amplifier to ensure you get a good image, and how often is the equipment calibrated?
So for GE, there is a RF calibration tool with a dummy load and a watt meter to where we will set the RF output to a specific wattage. So we set the output to 16 kW on the body and 2 kW for the head area. And on the Siemens MRI, they have built-in dummy load, so you don't have to install any other equipment to do it. So there's calibrations in the tune-up procedures, and there's also checks for the calibration and the QA process.
Great, thank you. Another question here is, what is the MRI room shielded with?
So the MRI room is shielded with copper, or or some rooms also use things like stainless steel, with it's got the particle board in between it, and it's sandwiched in between two layers of metal. So there's an important thing also is that you do not want to, put a screw or anything through the MR shielding, because that could cause leakage, or it could also cause your shield to be grounded. So if you ground it, it's going to cause some issues with your scanning images. Your SNR values will go down, and it's kind of a big issue. So you don't want to have any penetration in that shielded room.
Okay, and one more question before we kind of wrap up, Ed. Are there any new or upcoming MRI technologies that would be considered significant improvements or major advancements to mention that didn't exist 10 years ago?
Yeah, I mean, there are some new magnets being developed that are using a very low amount of cryogens, and they're in sealed vessels. Very interesting, because so you still have the cold heads and the compressors that are used to, maintain stuff, but they don't require any venting pipes in the event of a quench. What happens with those is that there's a external vessel around the inner MR, and it contains those gases. And what will happen is that the cold head will recondense that gas back into a liquid, and all this is internal to the magnet. So you don't have any helium loss. So right now, helium's very expensive. It's over $30 a liter. So when you're talking about refilling a magnet, you're usually using somewhere around 500 to 750 liters. So if you do the math, that's pretty expensive, just for a fill. Zero boil offs are great, but these other magnets are definitely going to be a game changer.
Sounds great. Thank you, Ed. Thanks for your time today, Ed, and for a really informative presentation, which I hope you all enjoyed. I'd like to encourage everyone to visit today's sponsor's website at allpartsmedical.com to learn more about the services they provide for our industry. As promised, the answer to today's trivia question is Coca-Cola, so congratulations to our winner, Adam Treslam. Just a quick reminder, you can attain your CE certificate by completing the post-webinar survey. The survey will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@ndpublishing.com. We'll be back next week with another webinar, so please visit webinarwednesday.live for more details and complimentary registration. Thank you all once again for your time today, and I hope you enjoy the rest of your day.